Welcome, everyone. It is a pleasure to have you here today. Our focus for this session is the Essential Algorithmic Toolkit. We will be exploring the core patterns essential for writing efficient code and mastering technical interviews. By understanding these fundamental algorithmic strategies, you will gain the insight needed to solve complex problems and optimize performance in your software development journey. Let's begin building your professional toolkit for success. Mastering the fundamentals is the most critical step for any junior developer. While it can be tempting to dive into complex, obscure algorithms, the real value lies in a solid understanding of core principles. This foundation is essential to write efficient production code that is both performance and maintainable. It also allows you to understand how underlying data structures behave, ensuring you make the right technical choices for your projects. Furthermore, mastering these basics will empower you to pass technical interviews with confidence. By focusing on these core pillars, you set yourself up for long-term success in the field. Searching algorithms are a fundamental component of computer science and data management. Understanding how to find specific data efficiently is essential knowledge that every developer should master from day one. In this section, we will explore the various techniques used to navigate through data structures to locate information quickly and effectively, minimizing the computational resources required for the task. Let's examine the differences between linear search and binary search. On the left, we see linear search, which functions by checking each element in a dataset one by one. While this approach is simple to understand and implement, it becomes increasingly slow as datasets grow larger. Its time complexity is O of n, meaning the search time increases linearly with the number of items. On the right, we have binary search. This algorithm is designed to find an item in a sorted array by repeatedly dividing the search interval in half. By eliminating half of the remaining elements with each step, it achieves a much more efficient time complexity of O of log n. Because of this logarithmic efficiency, binary search is considered the most important search algorithm to master, as it remains incredibly fast, even when dealing with massive amounts of data. Sorting algorithms represent one of the most fundamental concepts in computer science, serving as a primary tool for teaching algorithmic efficiency. At their core, these processes involve rearranging a collection of data into a specific order, such as numerical or alphabetical. By examining how different algorithms approach this task, we can better understand the trade-offs between speed and resource consumption, providing a critical foundation for optimizing complex systems. While you will rarely need to write a sorting algorithm from scratch in a production environment due to highly optimized built-in methods, understanding the mechanics of these fundamental algorithms is essential. On the left, we have merge sort, a definitive example of the divide and conquer paradigm. It functions by recursively splitting an array into halves, sorting those subarrays, and then merging them back together. Its primary advantage is a guaranteed time complexity of O of n log n, providing predictable performance even with large datasets. On the right, we see quicksort, which operates by selecting a pivot element and partitioning the array around it. Elements smaller than the pivot are moved to one side, and larger elements to the other. Although its worst-case time complexity is O of n squared, quicksort is frequently faster in practice than merge sort due to lower constant factors and better cache efficiency. Choosing between these often involves a trade-off between merge sort's stable, guaranteed performance and quicksort's superior average case speed. To build a solid foundation in computer science, we must first establish a conceptual baseline by understanding simpler sorting algorithms like bubble sort and insertion sort. While these methods are rarely the most efficient choice for large datasets, they are essential for your theoretical knowledge. You need to understand these algorithms primarily so you can explain exactly why they are considered inefficient compared to more advanced techniques like merge sort or quicksort. As shown here, these simpler sorts operate with a time complexity of O of n squared. Recognizing this quadratic growth is key to articulating the trade-offs involved in algorithmic design and choosing the right tool for the job. Tree and graph traversal are foundational concepts in computer science, providing the systematic methods required to visit every node within a data structure. These techniques are critical for navigating real-world data connections, ranging from the hierarchical organization of file systems to the complex, interconnected webs of social networks and global navigation maps. By mastering these traversal algorithms, we can efficiently extract insights, perform searches, and optimize paths within intricate data environments. Today, we will explore how these mathematical structures allow us to model and navigate the sophisticated relationships that define our digital landscape. Many real-world problems, ranging from social network analysis to network routing, are effectively modeled using mathematical structures like trees and graphs. When traversing these structures, we typically choose between two fundamental algorithms: breadth-first search and depth-first search. Breadth-first search, or BFS, explores the graph level by level, moving horizontally across each tier before descending further. Because it examines all neighbors at a given distance first, it is the optimal choice for finding the shortest path on unweighted graphs. In contrast, depth-first search, or DFS, explores as far down a single branch as possible before backtracking to pursue alternative paths. This methodology is heavily utilized in complex puzzles, maze navigation, and for discovering connected components within a larger dataset. Practical problem-solving patterns represent the essential algorithmic toolkit utilized to navigate complex coding challenges and optimize the logic behind everyday software solutions. By mastering these recurring patterns, developers can move beyond trial and error, employing proven strategies to create more efficient and scalable code. This session explores the core techniques that serve as the foundational building blocks for modern algorithmic thinking. Core algorithmic patterns provide a structured way to approach and solve programming challenges efficiently. On this slide, we examine two fundamental techniques. First is the two-pointers pattern. This strategy employs two variables to iterate through a data structure, typically from opposite ends moving inward or by moving at different speeds. It is a highly effective method for finding pairs in a sorted array or reversing a string in place, allowing us to process data with minimal overhead. Second, we have the sliding window pattern. This involves defining a specific range, or window, over an array or string and shifting it across the dataset. This is the primary solution for problems involving contiguous elements, such as identifying the longest substring with specific properties or calculating the maximum sum of a subarray. By only updating the window as it moves, we significantly optimize the computational process. Hashing techniques, such as maps and sets, are powerful tools for optimizing algorithms by using dictionaries or objects to store item frequencies and track scene elements. The illustration demonstrates how a disorganized stream of data can be funneled into a structured table, where shapes serve as keys and their counts serve as values. This pattern represents a fundamental trade-off. We utilize additional memory space to achieve a drastic reduction in time complexity. By leveraging constant time lookups, we can often transform an inefficient O(n)² process into a much faster O(n) operation, making it essential for handling large-scale datasets efficiently. When analyzing algorithmic efficiency, we must adhere to the fundamental principles of Big O notation. This golden rule focuses on how the execution time or space requirements of an algorithm scale as the input size grows toward infinity. By simplifying complex expressions and focusing on the dominant terms, we gain a clear mathematical understanding of performance bottlenecks and scalability, allowing us to make informed decisions about algorithm selection in real-world software engineering. To effectively utilize algorithms, a developer must possess a solid understanding of Big O notation. This framework serves as the standard language for measuring how system demands scale alongside data growth. Specifically, we analyze time complexity to determine how an algorithm's runtime increases and space complexity to track its memory consumption. As illustrated by the graph, the performance impact of these complexities varies significantly. While constant or logarithmic growth, denoted by O of 1 and O of log n, represents optimal efficiency, linear O of n growth scales proportionally with data. In contrast, O of n² illustrates quadratic growth, where execution time rises sharply, making it far less efficient for large-scale datasets. The developer's arsenal represents the foundational skill set essential for every modern engineer. These core competencies, ranging from analytical investigation and performance optimization to the mastery of interconnected data structures, form the basis of technical excellence. By focusing on these fundamental pillars, you will be equipped to build efficient logic, understand complex underlying architectures, and excel in high-level technical problem-solving. These are the tools that transform abstract concepts into robust, scalable solutions.